Hello guys, myself Guna. Me and my teammates Ritika and Vaishnavi will be explaining about how QUIC takes care of congestion control and loss detection, and also how TCP controls loss detection and congestion control by taking suitable codes. And first, we will be explaining about QUIC and QUIC congestion control techniques, QUIC loss detection techniques, and also in the later stages, we'll be showing a code and we'll be executing two codes, which is the client server code of QUIC and TCP, and we'll be evaluating the results so that you guys will get a clear understanding and on how TCP and QUIC performs loss detection and congestion control. So we have taken a research paper which is quick loss detection and congestion control, and we'll be first explaining that paper, and later on we'll be showing the codes and executing the program so that you guys will understand. So let's start. The title of the research paper which we have selected is quick loss detection and congestion control. Myself Guna, Vaishnavi, Ritika, we will be explaining each and every part of this research paper. So these are the topics that we'll be discussing in the later slides. So when I talk about the introduction of this research paper, Quick UDP internet connection is a transport layer protocol which sits underneath HTTP and runs over UDP, as you can see here. And it is already seeing a widespread deployment in many Google servers, Chrome, and also mobile YouTube app. And it also being standardized in IETF. From a technical point of view, there's nothing much to learn about Quick as it adopts many approaches from TCP like reliable data transfer, congestion control, flow control, etc. So what made us select this topic and what made Quick special? So as we have all learned, TCP's flow control, congestion control, reliable data transfer. We all write at home with Quick. So we don't need to talk about any of these topics, but we should put on a word on Quick connection establishment and how Quick multiplexes multiple application streams over a single Quick connection. Uh, as TCP, QUIC is a connection-oriented protocol. It uses connection handshaking protocol between two endpoints, which is between sender and receiver, for reliable data transfer, security, etc. In the traditional HTTP, what happens is that TCP first sends a handshake, which takes one full RTT, and above TCP it sends TLS, which again takes one other full RTT. So two RTTs are required to transfer data in TCP, whereas in Quick, as it uses UDP, in only one handshake, it uses all these things like reliable data transfer, flow control, congestion control. All of these things will be sent in only one data packet. So, and also, as you can see here, there are three packets which have to be sent from this side to this side. And when the first packet goes, and if any error occurs in TCP reliable data transfer, it blocks the other two streams, which is known as head of the line blocking. This has been solved in TCP, where each packet gets its own encryption level, reliable data transfer level, and also a congestion control level. So these three packets, when they are transferring, and if any stream gets an error, it will not block the other two streams. So the other two packets will be sent securely. So here are the four main differences between TCP and QUIC. First is separate packet number spaces. QUIC uses packet numbers assigned for each packet, whereas TCP uses sequence number assigned for each byte of the data. And second is no reneging. QUIC does not allow the reneging of packet acknowledgements, simplifying implementations and reducing memory pressure on senders compared to TCP acknowledgements. And the third one is probe timeout replaces RTO and TLP. QUIC utilizes a probe timeout mechanism, avoiding unnecessary congestion window reductions and providing more aggressive recovery than TCP in certain scenarios. And fourth one is handshake packets are not special. TCP does not encrypt data unless it has computed two RTTs, whereas QUIC encrypts data from the first handshake packet itself. Now the later slides will be explained by Vaishnavi and Ritika.
When it comes to loss detection, we can understand loss detection in quick in 3 points. When we are identifying and recovering of the lost packets and operating per packet number space, where it helps the loss detection in quick. And also the second important point is acknowledgement based loss detection. Follows TCP's fast retransmit and early retransmit principles and also declares packet loss based on the factors like acknowledgement status, packet count, and time thresholds. Probe timeout mechanism, triggering sending probe packets when acknowledgements are not received within the expected time. These points helps us ensure the loss detection in quick. Moving on to the next slide. In congestion control in quick, there are four main points apart from the points displayed here. Algorithm flexibility, acknowledgement only packets, and per path congestion control, and also window constraints, where few of these are already mentioned in those five of the points which are been showing on the presentation. But then these are the points I would like to speak about. Algorithm flexibility. Quick allows choosing different congestion control algorithms. You can choose whatever algorithm you can when it comes to congestion controls. And when it comes to acknowledgement only packets, packets with only acknowledgement frames do not contribute to the congestion, but also help detect losses. Per path congestion control. The congestion controller operates on per path basis. Explicit congestion notification is also supported, which is ECN. And window considerations are initial congestion window values and minimum congestion window guidelines are provided. This is all about the congestion control. Now, Pritika will carry on with other topics.
So let us look into a few security considerations for QUIC. QUIC itself is a combination of several security features that is inbuilt in it, but there are also specific security considerations that should be taken into account while implementing or while you are deploying QUIC. The first one is loss and congestion signals. QUIC being a separate transport protocol from TCP, and it also coexisted with the TCP flow. Because it is separate, it has its own congestion control mechanisms and its own packet loss mechanisms, whereas it adjusts its sending rate based on the set of algorithms it has and also the feedback it gains. So what happens here is when it coexists with TCP flow, it affects the fairness and efficiency of that particular network. For the second point, we have middle box interference. Now, QUIC is very relatively new when compared to TCP. So, networking equipments such as firewalls, proxies, or other middle boxes may not be designed to handle this QUIC protocol efficiently. This lack of the support can lead to interoperability issues and potentially disrupt communication between clients and servers using QUIC. The third one is multiplexing of streams. QUIC allows multiple streams of data to be sent coherently within a single connection. This can complicate the traffic analysis and monitoring. So, the potential attack which can happen is like an attacker can hide malicious activities within a stream of legitimate data. And then the last security concern we're going to address here is zero round trip time. QUIC allows for zero RTT, it is very famous for it, to reduce the latencies. This is beneficial for its performance because the latency is reduced. It introduced, but the possible attacks are here are replay attacks, as the same data can be sent multiple times without re-authentication. Now, let us look at additional topics for inclusion. We have gone through the protocol and we have brainstormed few ideas, and we thought these might be relevant to be added into the current existing QUIC protocol. The first one we thought about is support for Internet of Things devices. As we know, IoT devices are very profound nowadays. It is in everything. It is implemented worldwide, and it's already the trend here. So we can add additional features that can specifically cater to this particular devices to constraint and requirements of IoT communications can be valuable. This may involve optimizing for low power and low bandwidth scenarios as well as mechanisms for efficient communication in IoT deployment. The second idea we thought about is multipath support. Adding native support for multiple communications would allow QUIC to utilize multiple network paths simultaneously. This can enhance reliability, throughput, and fault tolerance, particularly in scenarios where devices have multiple network interfaces or when they are diverse routes to the destination. So our paper went through the QUIC protocol. It told us how it's differentiated from TCP, and the author also mentioned few loss detection pseudocodes and congestion control pseudocodes. So let's go through them. First, here we have the loss detection pseudocode. Initially, as you can see here, the left part of the code is the initialization part, where we initialize various variables related to loss detection, congestion control, including its timers, triggers, and clocks. Here we also initialize few variables with an initial value such as smoothed RTT and RTT VAR. Um, and then after you specify all this, we next have the on packet send function. Here the on packet send function records information about a send packet, including its packet number, time sent, whether it's acknowledgement eliciting, whether it is in flight, and the number of bytes sent. So what does it do here is, uh, so when it is in flight, if the packet is in flight, the acknowledgement eliciting, it updates the time for the last acknowledgement eliciting packet and triggers congestion control actions, or else it just sets the loss detection timer. The next function we have is on datagram received. Now this handles the reception of a datagram. If the server's was an anti-amplification limit, it sets the loss detection timer and triggers the loss detection timeout if the timer has already expired. Now you then have the biggest function you can see here is the on loss detection timeout function. What this does is, it determines the earliest loss time and the corresponding packet number space. If there are lots of packets based on the time threshold, then it performs a loss detection, marks the packet as lost, then it triggers an action for the lost path and sets the loss detection timer. If then you have another case, if no acknowledgement eliciting packets are in flight, then it handles a specific case related to address validation. Otherwise, it deals with the probe timeout. It sends new data if available, retransmits old data if not, and increments the probe timer count. And then it sets the loss detection timer. Now let's look at the congestion control pseudocode. In congestion control pseudocode, we have is similarly, we just have the initialization phase. Here, the initialization variables related to the congestion control, we have those are congestion window. Congestion window size is basically how much can the congestion hold, how many bytes and all that, the bytes in flight, congestion recovery, start time, and so on. Then we have counters initialized for different packet numbers. Here that is EC and CE counters where PN space is initialized to 0. And then we have on packet send function. When a packet, this function, what it does is when a packet is sent, its size is added to the total bytes in flight. This is part of tracking the amount of data that is actively in transit in network. Then we have on packet loss function. That's probably in the next slide. Yeah. So the on packet loss function, when packets are lost, their size is subtracted from the total bytes in flight. If in flight packets were lost, a congestion event is triggered and the time of the last loss is recorded. It checks if the loss of these packets indicates persistent congestion. If so, it resets the congestion window and congestion recovery start time. That's all we have about the pseudocodes here, and then my teammate will go on with our implementation.
So this is the implementation of our program. I've created two programs, which is QUIC client server and another one is TCP client server. I've created these two programs because to show efficiently how QUIC operates congestion control and how TCP performs congestion control. QUIC uses QUIC algorithm, as you can see here. QUIC algorithm for congestion control, whereas TCP uses traditional way of incrementing and starting the slow starting from the slow start. So first I'll be implementing this QUIC client server. Here is my server code, which will listen on a specified a specified port, and it waits for the client to connect, and the client sends 5 packets, which is ABCDE, and also it performs when acknowledgement release the congestion window. It will print all those things. Okay, so now I'm implementing the server, as you can see down here. QUIC server, it started listening. Yeah, so it have started. I mean, it has started sending packets A, and it also received acknowledgement for packet A. Same case with A, B, C, D, E. If I look onto the server, see, at the end, it received all the packets A, B, C, D, and E. Oh, wait. Yeah. So it also prints the congestion window size here for every acknowledgement received, and also if any packet is lost or if any packet does not receive any acknowledgement, it immediately retransmit. It does not wait like TCP until and unless a specific timeout. It will retransmit the packet in TCP, but in QUIC it does not wait for a specific time. It automatically retransmit the data if acknowledgement is not released. So as you can see here, no acknowledgement received for a packet which is C. So it retransmits within a moment of time. It retransmits in the next moment because it does not receive an acknowledgement. And also I have kept a list, I have kept a track of acknowledgement packets and unacknowledgement packets for every step. So that I can keep track of what packets I have received acknowledgement and what packet does not receive an acknowledgement. So this is how it works. And if I talk about the quick connection.py, the main code, yeah. So at the start we have initialized a few variables. I have started taking a condition window of size 4 here, and also this is the send packet function. When the client wants to send a packet, it triggers this function and it sends the packet to the server and receive acknowledgement. This is the main part of the code. In main part of the code, and here only our condition control code is present here. And here, as you can see, from here, as you can see, uh, the code checks if the current congestion window is less than the slow start threshold. If it is the case, then it will increase the congestion window by 1, implementing the slow start phase of the congestion control algorithm. And next, if the congestion window is greater than equal to the threshold, then we'll enter into this code where congestion window is greater than equal to the slow start threshold. The code enters the congestion avoidance phase using the QUIC algorithm. It calculates the elapsed time since the last acknowledgement. Then it computes the QUIC window size based on the QUIC algorithm formula, which is this QUIC algorithm formula, which I have highlighted here. And then next, it updates the congestion window to the calculated QUIC window size. Otherwise, it increases the congestion window by a fraction. Here, it increases by the fraction of it. And next, the system implements the QUIC algorithm for adjusting the congestion window size to the optimize data transmission and avoid network congestions. So this is the main part where the whole program stays on. And also, if I show you the TCP server client program, this TCP server, same like QUIC server, it listens on a specified port, and this is the client. This is the client where it's in the 5 packets, and also I have the main TCP connection code. Yeah, I have the main TCP connection code. Here also I have taken the connection window of size 4 only, whereas see, it does not use QUIC algorithm because TCP does not support QUIC algorithm. It uses traditional way of congestion control. And yeah, if I start running this. Yeah, I've executed the server first. It is listening on a specified port and TCP client. Yeah, it has sent 5 packets A, B, C, D, and it got disconnect. I mean, it will disconnect automatically. And here on the server side, yeah, this here the last A, B, C, D, and E. It have received 5 packets. Here in TCP, I have pasted the same condition window for every successful acknowledgement received, and also the dynamic RTT for every successful acknowledgement received. And also same case here, if a packet is not acknowledged, okay, no acknowledged packet for received data C, it will retransmit the packet, but it will wait for a certain period of time, and then it calls the retransmission method down there. So if I go into the code and explain, yeah, one sec. Actually, I've taken some notes here. So yeah. So the starting initial phase, which is all same like QUIC, I have initialized a few initial values, which is the condition window phase and the self RTT of 0.2. I've taken 0.2, and also the alpha value, which is 0.125, which is used for RTT calculation, EWMA. So the send packet when it is called by the client. And next, there is the congestion control phase, where the main code of the program here. And here, starting from this, our code starts the congestion control phase, which is if an acknowledgement is received, it increments the expected ACK value by 1, and also updates the list of unacknowledged packets. If it is updates the list of unacknowledged packets that I have received an acknowledgement, so remove that thing from the unacknowledgement list. And and also, if the current congestion window size is less than the slow start threshold, uh, then it increments the congestion window by 1, implementing the slow start phase. Otherwise, it increments the congestion window using a formula for congestion avoidance, which is this congestion avoidance formula. And next, also, if no acknowledgement is received, it will wait for a certain period of time, which I gave for 0.5 seconds. Then it updates the expected ACK to the packet number and reaches the congestion window to 1. It also filters out unacknowledged packets that have a packet number less than the received packet numbers. And also, the last step, this code tells us that it retransmit all unacknowledged packets using the retransmit method here. So the major difference I would like to say is here, when I keep side by side, yeah, as you can see here, it uses a specific formula for congestion window avoidance phase. It uses specific cubic formula, and whereas TCP uses another formula, which is this one. And also, in the loss detection or retransmission phase, QUIC does not wait for a specific period of time, whereas TCP waits for a specific period of time and then retransmit the packets. So this is the basic implementation of QUIC and TCP for the, I mean, for the explanation purpose, for easy purpose, I have taken these two codes from various research papers. But to implement this in real world, we need to add on more methods, such as encryption, and also according to various network needs, we have to change this code. Yeah, we have to change this code for various network needs. So this is our this is our presentation and a presentation on how QUIC performs congestion control and loss detection, and how TCP performs congestion control and loss detection. We want to show the clear difference by using a code piece. So yeah, thank you guys.